Do you want to perform sophisticated what-if analysis operations on your data, such as statistical, engineering, and regression analysis? Or do you want to keep track of items in a simple list, either for your personal use or for limited collaboration purposes? Well, data analysis in Microsoft Excel is just for you. Hi guys, it's AnOVa here, and for today's video, we are going to talk about data analysis.
What is data analysis?
Data analysis is a process of systematically applying statistical and logical techniques in order to describe and illustrate, to conclude and recap, and to evaluate data. The analysis toolpack in Microsoft Excel includes the tools such as AnOVa, Correlation, Covariance, Descriptive Statistics, Exponential Smoothing, F-test2 sample for variances, Fourier Analysis, Histogram, Moving Average, Random Number Generation, Rank and Percentile, Regression, Sampling, T-test, and Z-test. To access these tools, click on Data tab and look for Data Analysis. And there you have it. Now let's dig into these tools. First we have AnOVa. AnOVa stands for Analysis of Variance. It is a statistical method that separates observed variance data into components to use in additional tests. Under AnOVa, we have three kinds. First, we have the AnOVa single factor. Second, a two-way AnOVa with replication. And third, a two-way AnOVa without replication. AnOVa single factor, or also called as one-way AnOVa, is used to determine whether there are any statistically significant difference between the means of three or more independent or unrelated groups. In our example, three columns contain standardized test scores in mathematics from the three sections A, B, and C. To solve for one-way AnOVa, click on Data and then look for Data Analysis. Choose AnOVa single factor. Our input range are all our data starting from section A to section C. Group by columns and labels in first row, since we've included the labels section A, B, and C. Leave the alpha level at 0.05 and our output range, click on any vacant cell. Click OK, and there you have it. A two-way AnOVa with replication is performed when you have two groups and the individuals in that groups are doing more than one thing. In the following example, we have two groups of data from two schools, School A and School B. And a group of 12 students took math, science, and English standardized tests. We use a two-way AnOVa with replication because we've got two groups and they are doing more than one thing. To solve for a two-way AnOVa with replication, click on Data tab and choose Data Analysis. Look for an AnOVa two-factor with replication. Select all the data including the labels for our input range. For the rows per sample, it is the number of students per school who took the tests. So it is 12. Still, our alpha level is 0.05 and our output range, just click on any vacant cell. Click OK, and then there you have it. Next, we have a two-way AnOVa without replication. A two-way AnOVa in Excel without replication can compare a group of individuals performing more than one task. For example, you could compare student scores across from the three subjects, Math, Science, and English. In the Data Analysis tab, look for AnOVa two-factor without replication. Select our input range and check on the labels if you included the labels Student, Math, Science, and English. Our alpha level is 0.05 still, and our output range, just click on any vacant cell again. Tap OK to have the results. The two most important factors in using AnOVa to accept or reject the null hypothesis are: first, if the F value is larger than the F critical value, that will lead you to reject the null hypothesis. Second, if the P value is smaller than your chosen alpha level, that would also lead you to reject the null hypothesis. Next one, we have correlation. Correlation concisely describes the degree and direction of the relationship that exists between two variables. The value of any correlation coefficient must be between -1 and +1 inclusive. For our example, we want to know if there are any relationship between the two variables, number of hours studied, and the exam scores. To solve for it, let's go to data analysis and choose correlation. In the input range, we must select all of our data. If we want to check the labels in the first row, include the labels, but if not, never mind. For the output range, click on any vacant cell and then click OK. And that is the correlation. The correlation coefficient that is solved is approximately 0.98. This means that there is a high positive correlation between the number of hours studied and the exam scores. This implies that if the number of hours studied increases, the exam scores also increases, and vice versa. If the number of hours studied decreases, the exam scores decreases. And that is all about correlation. Then we have covariance. Covariance is a measure of how much two random variables vary together. It can be used in the same setting as correlation. However, covariance are not scaled, meaning to say the coefficients doesn't lie between -1 and +1 only. Let us use the same data from our correlation example to see the difference. Again, in the Data Analysis tab, choose Covariance. Fill in the needed information just like what we did in correlation. As you can see in the results, the computed covariance between number of hours studied and exam scores is approximately 43 compared to the computed correlation coefficient, which is approximately 0.97. And that is how covariance works in data analysis. Descriptive statistics. The descriptive statistics analysis tools generate a report of univariate statistics for data in the input range, providing information of central tendency and variability of your data. Let's have an example. Under the Data Analysis tab, choose Descriptive Statistics. Put the input range and group by columns. We've included the labels, so we must check the labels in that column. Our output range, we must click again on any vacant cell within that Excel. Choose at least one statistical option. Now let us click on this summary statistics. Click OK and wait for the results. And there you have it. The descriptive statistics includes the mean, standard error, median and mode, standard deviation, sample variance, and more. Now what if we have 3 sets of data? Can we still do descriptive statistics? Of course, yes. For our example, we have 3 sets of data from Section A, Section B, and Section C. Now to solve for descriptive statistics, just click on Data and choose Data Analysis. Look for Descriptive Statistics in the dialog box and click OK. For our input range, select all the data and including the labels. So we must check the labels in the first row. For our output range, click on any vacant cell and then choose at least one statistical option. So for this, let us check the summary statistics. And there you go. We have now the results of the central tendency, which are the mean, median, and mode, and of course the variances, which are the standard deviation, variance, range, and etc. Exponential smoothing. The exponential analysis tool predicts a value that is based on the forecast in that prior period adjusted for the error in that prior forecast.
Let us perform exponential smoothing using data analysis. Choose exponential smoothing under data analysis. And for our input range, it is the actual data. Select the actual data. And then the damping factor is 1 minus the alpha level. So the value of our damping factor must be 0 to 1. I put here 0.9 for example, and check the labels, and for the output range, click on any cell. I check the chart output so that I can see the graph of this exponential smoothing. And there's the result. The graph of the blue line is the original data, while the orange is the exponentially smooth graph. Using the damping factor of 0.9, we can see that there is an upward trend in the forecast. Now let us use 0.2 as the value of the smoothing constant. This is a reasonable smoothing constant so that we can see a more reliable graph. And now as you can see, the trend goes downward at the end. Next we have the F-test 2 sample for variances.
The F-test 2 sample for variances analysis tool performs a 2-sample F-test to compare two population variances.
Again, if the calculated F value is less than the F critical value, then the null hypothesis is accepted. Our null hypothesis is the variances are equal. Let us try to solve using data analysis. Under data analysis tab, choose F-test 2 sample for variances. In the input, we have variable 1 range and variable 2 range. Variable 1 range are the section A, which means the first set of variables, and our variable 2 range is the section B, or the second set of variables. I checked the label since I included it. The alpha level is 0.05, and for the output range, choose any vacant cell. Click OK, and there you have it. The calculated F value is 2.12, while the calculated F critical value is 3.14. This F value is less than F critical value, meaning to say the null hypothesis is accepted. That is, the variances of the two sets of data, section A and section B, are equal. The Fourier Analysis.
The Fourier Analysis tool solves problems in linear systems and analyzes periodic data by using the fast Fourier transform method or the FFT method to transform data.
This tool also supports inverse transformations, in which the inverse of transformed data returns the original data. In our example, I use 16 single set of data points under time. By the way, the Fourier Analysis Excel tool has a couple of limitations. The maximum number of points is 4096 because it is the limit of data amount that Excel can accept. And the data points must be in the powers of 2. In other words, you can only enter 2, 4, 8, 16, 32, and so on up to 4096 numbers. Next, we have histogram.
The histogram analysis tool calculates individual and cumulative frequencies for a cell range of data and data bins. This tool generates data for a number of occurrences of a value in a data set.
Let's have an example. The first column is the student's scores in math quiz, while the second column is the bins. Bins are important in performing histogram analysis. Bins are the number that represents the intervals into which you want to group that source of data. Now to perform, click the data analysis and choose histogram. Fill in the necessary informations and check the boxes if you want to. Then click OK to have the matrix and the graph. Moving average.
Similar to the exponential smoothing, the moving average analysis tool projects values in the forecast period. It is based on the average value of the variable over a specific number of preceding periods.
Use this tool to forecast sales, inventory, and other trends. Now let us try to perform moving average in data analysis. Click the Data tab and choose for Data Analysis. Under Data Analysis, look for Moving Average. For our input range, we only select the number of enrollees column. For the interval, I use 5. This means that I use 5 previous data points to calculate the moving average. The higher the interval number, the smoother the peaks and valleys. Click on any vacant cell for the output range. And you can check chart output and standard errors if you want to. Click OK so that the answer will be shown. Now you can observe that the first 4 points is marked as NA. It is because it cannot compute the first 4 points because there are not enough data points. That is all for moving average. Now let's move to another data analysis tool, random number generation. The random number generation analysis tool fills a range of independent random numbers that are drawn from one of the several distributions. Now, as you can see for our example, there are no data yet. And that is how random number generation works. Just look for random number generation under data analysis. And as you can see, there are number of variables and number of random numbers. Number of variables are the number of columns you want your data to appear in, while the number of random numbers are the number of random numbers that will appear in each column. In the distribution, you can choose under uniform, normal, and etc. Let us try uniform. Now I want my data to be in between 0 to 100. I left the random seed and field, and for the outer range, I click any vacant cell in the sheet. Now let's try another one. At this time, I want my distribution to be a normal distribution. There, as you can see, there's a mean and standard deviation. I put 100 as my mean and my standard deviation as 15. I left the random seed unfilled again, and for the output range, I clicked on any vacant cell. And that's how easy to generate random numbers using random number generation under data analysis. Then we have the rank and percentile. The rank and percentile analysis tool produces a table that contains the ordinal and the percentage rank of each value in the dataset. Let us take a look at an example. For the first column are the students. I use numbers for characterization. And for the second column are their corresponding scores. Now, to perform rank and percentile data analysis tool, just go to data analysis and look for rank and percentile. And for the input range, just select only the scores of the students. Click any vacant cell for the output range and click OK. And there, as you can see in the results, the point, the scores, the rank, and the percentage. 0.7 means the 7th student on the list who scored 95 ranked first, having a percentage of 100. Same as 0.8, it is the 8th student on the list, and so on and so forth. And that's how rank and percentile in data analysis works. Regression. The regression analysis tool performs a linear regression analysis by using least squares method to fit a line through a set of observations. For our example, I use the number of hours studied and exam scores. To perform regression analysis, just click on Data tab and Data Analysis. Under Data Analysis, choose Regression. Now we have here the input Y range and the input X range. Input Y range is the predictor variable, or also called as the dependent variable. So for our data, the exam scores is the dependent variable. While the X range or input X range are the explanatory variables or the independent variables. Meaning to say that the number of hours studied in our data is the input X range. And for the output range, click on any vacant cell. You can choose residuals below and click OK. And there you have it, the results of regression analysis. Now under regression analysis, we have simple and multiple regression. First, let us have the simple linear regression. In simple linear regression, it allows us to summarize and study relationships between two continuous variables. Let's take a look back at our previous example. As I have said earlier, the study R's is the explanatory variable or the independent variable, which is also the X. And the exam score is the predictor variable or the dependent variable Y. To solve for the regression, just click on Data Analysis under Data tab, and in the dialog box, look for Regression. Our input Y range are the exam scores and our input X range are the study R's. Check the labels since we've included the column titles. For the output range, click on any vacant cell and it's up to you if you want to choose residuals and normal probability and etc. And then click OK for the results. Now the important terms here are the R squared, the adjusted R squared, the significance F, and the coefficients, and the p-value. R squared is the percent of variance in Y explained by the variance in X. And the adjusted R squared is a modified version of the R squared that has been adjusted for the number of predictors in the model. We also need the significance F. It has a similar interpretation with that of the p-value, however, the key difference is that significance F applies to the entire model as a whole, whereas the p-value will be applied only to each corresponding coefficient. Now let us try to construct a simple linear regression model for this one. Just click on the Insert tab and select Scatter, and you will choose what graph you want. In here it shows a blank graph, so we must select our data. Select all our data and then switch rows and columns. Now I want my graph to be customized, having the main title and the axis titles. To add a line for our graph, just click on the plot and then choose the layout up there. Click on trend line and more trend line. Select linear and check on the box for the display equation in the chart and display R squared value on chart. And there's our simple linear regression model, including the equation and the value of the R squared. The linear equation in slope-intercept form is y is equal to 5.33x plus 46.82. If you observe what we solved earlier using the regression in data analysis, the coefficient of study R's is the slope of our equation. And also the intercept is the intercept of our equation, which is 46.82 approximately. And of course, we have the same value of R squared, which is 0.9463, meaning to say that there are 94.63% of variance in exam scores explained by the variance in study R's. The next one under regression is the multiple linear regression. Multiple linear regression, or also known simply as multiple regression, is a statistical technique that uses several explanatory variables to predict the outcome of a response variable. Yes, you can use more than one independent variable, or the X range. However, take note that you can only use one dependent variable, or the Y range. Let us take a look on our example. In here, the number of hours studied, the anxiety level, the number of hours sleeping, and the mood is our explanatory or independent variable, and our predictor or dependent variable is the exam score. Again, go to Data Analysis and choose Regression. For our input Y range, that is the dependent variable. You can only input one Y range, which is the exam score. And for our input X range, choose all our independent variables and then check the labels, and for the output range, click on any vacant cell. Just like the simple regression, the important factors here are the R square and the adjusted R square, the significance F level, and the coefficients and the p-value. And in here we have the equation for the multiple linear regression. Y is equal to beta sub 0 plus beta sub 1 times x sub 1 plus beta sub 2 times x sub 2 plus beta sub n times x sub n. Our beta sub 0 is the constant or the intercept Our x sub 1, x sub 2, and so on are the coefficients of our independent variables or the slope of the line. Now, the p-value of the independent variable mood is more than 0.05, which means that we don't need to include that in our computation. Now, let us do a prediction on one of the sets of data. We must plug into the number of hours sleep, 9, number of hours studied, 5, and anxiety level is 2. For our beta sub 0, or our constant, is the coefficient of the intercept. So let's begin. Type equal sign and then choose the coefficient of the intercept plus number of hours sleep times the coefficient of the number of hours sleep, or the slope of the number of hours sleep. And then next, the number of hours studied, and then times the coefficient or the slope of the number of hours studied, and click enter, and there's the result of our predictive analysis. Next, sampling.
The sampling analysis tool creates a sample from a population by treating the input range as a population.
Now let's see on how it works in Microsoft Excel. As for my data, I have the list of students and their gender. By clicking the sampling under data analysis, we have here the input range. Our input range are the numbers below the student. I checked on labels because I included the label. First, let us have the periodic. I will place 2 here, and for my output range, just click on any vacant cell. Tap OK, and there you have it. These are the students who will be my respondents. Let's try another one. At this time, I will be using random sampling. I wanted 10 random samples. For my output range, I click on any vacant cell and click OK. As you observe, numbers such as 5 and 20 are repeated. That is because random sampling in data analysis is with replacement. As a result, it's often better to use other approaches such as the generated Excel function, rand, open and close parentheses, t-test.
The two-sample t-test analysis tool tests for equality of the population means that underlie each sample.
There are 3 tools that employ different assumptions. First, the population variance are equal. Second, the population variance are not equal. And third, the 2 samples represent before treatment and after treatment observations on the same subject. T-test assuming equal variances.
This t-test form assumes that the 2 datasets came from a distribution with the same variances. It is referred to as homoscedastic t-test.
Now, the very first thing to do when performing a t-test is to solve for the f-test to sample for variances. It is to determine if they have equal variances or not. Let us take a look on this example. As you can see, our f value is 2.15 and our f critical is 2.72. F value is less than the f critical, meaning to say they have equal variances. That is when we are going to conduct the t-test to sample assuming equal variances. For our variable 1 range, select section A, and our variable 2 range is the section B. Hypothesized mean difference is still 0, and we are going to check the labels since we've included it. For our output range, just click on any vacant cell on this sheet. Click OK to have the results. T-test to sample assuming an equal variances.
This t-test form assumes that the 2 datasets came from a distribution with an equal variances. It is referred to as a heteroscedastic t-test.
t-test paired to sample for means.
You can use a paired test when there is a natural pairing of observations in the sample, such as when a small group is tested twice, like for example, before and after experiments.
In this case, we want to determine whether observations that are taken in the pre-test and observations that are taken in the post-test are likely to have come from distributions with equal population means. This t-test form does not assume that the variances of both populations are equal. That is why we are using t-test paired to sample for means. Variable 1 range are the observations that are taken before a treatment. In our case here, it is the data under pre-test scores. And our variable 2 range are the observations taken after the treatment, meaning to say, the post-test scores are our variable 2 range. In our hypothesized mean difference, we'll put here 0. I'll check the labels since I included the labels in the first place. For the output range, click on any vacant cell and then click OK. And we have now the results of t-test paired to sample for means. Again, we have to solve for the f-test to sample for variances to make sure that we are using the right t-test tool. Our f value is 2.96 and our f critical 1/tail is 2.76. F value is greater than the f critical value, meaning to say they have an unequal variances. It is therefore appropriate to use the t-test assuming unequal variances. For our variable 1 range, select the data on the column A, and then for our variable 2 range, select the data on our section B. Our hypothesized mean difference is still 0, and I'll check here the labels. For our output range, click on any vacant cell. Tap OK, and there you have it. And finally, we have the z-test to sample for means.
The z-test to sample for means analysis tool performs a two-sample z-test for means with known variances. It is performed instead of t-test if you have known variances and of course your sample size is greater than 30.
Now let's take a look on how to perform z-test to sample for means in data analysis. Well, in here, the population variance is still unknown, but the sample is already about 30. We have a sample of 40 students. So we must calculate for the population variance. To do it, just encode equal sign, var.p, open parentheses, and select the array, close parentheses, and then enter. Solve again for the population variance of the post-test scores. And there you have it. Now that we've identified our population variance, we can now proceed to the z-test. Look for z-test to sample for means and input our data. For our variable 1 variance, it is the population variance we've computed for the pre-test, and for the post-test population variance will be put on the variable 2 variance. After filling all the blank spaces, we have now the results of the z-test. Now let us have the reliability analysis using Cronbach'S alpha. Cronbach'S alpha represents the internal consistency or reliability associated with a particular scale. For our example, we want to analyze the reliability of our test questionnaire. In here, we have a whole bunch of data, and we have the questions 1 to 15 in the columns and students 1 to 30 in our row. Now, the numbers indicated here are their answers from a multiple choice test starting from 1, 2, 3, 4 or ABCD. Now, to perform Cronbach'S alpha, let's go to data analysis and solve for the AnOVa two-way factor without replication. Select our input range, however this time do not include any labels, just the data. Select any vacant cell for our output range. and then click OK for the answer. Now we have here the summary statistics for the rows and columns. And we also have here below the result of the AnOVa two-way factor without replication. Now to perform Cronbach'S alpha, we need to use the MS error and the MS rows. Because our formula for the Cronbach'S alpha is equal to 1 minus the quantity MS error over MS rows. And then let's solve for it. Just type equal sign and then 1 minus open parenthesis the quantity of MS error over the quantity of MS rows. And then close parenthesis, click OK. And there you have it. We have a value of 0.644 and so on. This means that our test is reliable. If it is 0.6C and above, the test is reliable. If the value ranges from 0 to 1, the closer the value to 1, the more reliable the test is.
And that's it for today's video. I hope you learned something. Thank you for watching.